Hi everyone, my name is Ben Wheatley, and our talk is entitled Modeling the Effect of Femoral Anteversion on Gait Dynamics and Patellofemoral Joint Loads. Lower limb joint pain is highly prevalent. For example, patellofemoral pain occurs in up to 25% of the general population. Lower limb torsion, such as femoral anteversion and retroversion, or tibial torsion, can cause gait impairment and joint pain, such as in the patellofemoral joint. The link between joint pain and torsion is unclear. However, there are factors including morphology, kinematics, muscle forces, as well as other biological factors. This talk is going to focus on the first three, and the goal of this work is to develop a modeling framework to study the effects of femoral anteversion on patellofemoral joint loads. Looking at our modeling overview, we began with the Rajagopal model and dataset. We then applied femoral anteversion from the baseline model all the way through an increase in femoral anteversion of 40 degrees in 10-degree increments. This is using Luca Modenese's recent work. We then applied MoCo to do actuator-driven tracking to generate gait kinematics and joint torques for our femoral anteversion models. And finally, we used these kinematics to do muscle-driven prescribed kinematic simulations in MoCo to calculate the joint reaction loads as a function of different muscle activity weights. This is using MoCo, and we did a Monte Carlo where we simulated 1,000 stance simulations for each anteversion model. So let's look a little bit more closely at our MoCo tracking problem. We began with our experimental markers from Rajagopal et al. We then used inverse kinematics tracking problem in MoCo to do our kinematics for a typically developing case. Then we combined these kinematics with the initial marker kinematics to use a MoCo problem that weighs both the marker and the kinematics to generate our femoral anteversion kinematics for our modified femoral anteversion models. So now we have lower limb kinematics for all 5 of our models, ranging from typically developing all the way up to an increase in femoral anteversion of 40 degrees. Looking next at our muscle-actuated Monte Carlo simulation in MoCo, we began with our femoral anteversion kinematics that we had just generated. We then weighed 7 sets of muscles or muscle groups using a Monte Carlo simulation of 1,000 simulations for each of our 5 femoral anteversion models. And then we output the patellofemoral joint reaction forces. And specifically, we're going to be looking at the root mean squared of muscle forces and the root mean squared of patellofemoral joint reaction forces across the stance phase. So let's go ahead and dive right into comparing our model to experimental data. What we're showing here is our model compared to data from McKay et al., a recently published paper that had gait kinematics and dynamics analysis for a cohort of typically developing group, as well as a cohort with a femoral anteversion angle of 38 degrees. This correlated very well with our femoral anteversion model of increase of 20 degrees, which is a total femoral anteversion of 37 degrees. So you can see here we're showing hip kinematics. This is hip flexion, hip adduction, and hip rotation as a function of stance phase. And what I want to focus on is the hip rotation. What we can see is there's an increase from the typically developing case, both for our experimental and solid and our model in dashed lines here, as we go from typically developing to an increase in femoral anteversion of 20 degrees. And so we have really good agreement here between our model and our experiment for our hip rotation kinematics. Then we have knee flexion, which does not see much of a change. And then finally, ankle kinematics of plantar flexion and subtalar inversion. And what we see here is there's an increase in that subtalar inversion angle, both across our experimental and our model data, although our model doesn't quite capture the shape of that subtalar inversion experimental data curve. Looking next at our dynamics, again, we have our hip dynamics up top. So these are the hip flexion, hip adduction, and hip rotation moments. And again, we see generally pretty good agreement between our model and our experiment. Moving on to our knee moment, we see that our knee moment is maybe a bit lower than the experiment from our model. One thing that I want to point out here is that we see a slight decrease from typically developing to our increased femoral anteversion experimental data in our knee moment. And then finally, looking at our ankle and subtalar moment, values, we have pretty good agreement overall with the shape of our model and our experimental curves. Generally speaking, maybe our model had a bit of an underrepresentation of the joint moments, but overall, pretty strong agreement here. Diving right into our preliminary Monte Carlo results, we're looking now at the patellofemoral joint reaction load. So this is the total load that is equal and opposite between the patellofemoral, or the patella, excuse me, and the femur at the patellofemoral joint. So as we increase from 0 to 40 degrees of additional femoral aneurysm from our typically developing case, we see that we have overall lower patellofemoral joint loads. So all 4 of our increased femoral aneurysm models actually had lower overall joint loads. However, if we look at the lateral patellofemoral reaction load, so this is now the contribution of this overall load that acts in the lateral medial direction, we see that that actually increases as we go from 0 to 10, as well as 20 and 30 and 40. So what we see overall is that with increased femoral aneurysm, the patellofemoral joint load decreased, but the load alignment worsened, meaning more of the load is actually being transmitted laterally, which can cause high contact pressure and could potentially lead to pain. Looking more carefully at our Monte Carlo results as a function of individual muscle force contributions, this graph on the left here is showing the rec-fem force root mean square in body weight, as well as the overall patellofemoral joint load. And so what we see is an increase in rectus femoris force leads to an increase in the patellofemoral joint. Not surprising there. If we look at the vastus lateralis muscle, again, generally we see that increases in vastus lateralis force lead to increases in patellofemoral joint load. These graphs here are just showing the ranges across our typically developing case, all the way to our bright red, which is our femoral aneurysm case of increased by 40 degrees. So overall, as expected, there were greater muscle forces that led to greater patellofemoral joint loads. Looking a little more closely at these data, we can see that we have linear fits between our rectus femoris force and our patellofemoral joint load. But now we're looking at our typically developing case and our most extreme case, where we have increased femoral aneurysm by 40 degrees. And again, we have an increase, as we have an increase in rectus femoris force, we see an increase in patellofemoral joint load, and that's pretty consistent across these 2 extreme femoral aneurysm angles. So the slopes really don't change that much as we go from typically developing all the way to this extreme case. However, if we look at the vastus lateralis muscle now, we can see that we actually observe quite a bit of a change in this relationship between muscle force and joint load. We can see that for the typically developing case, there's really very little increase in that joint load as a function of vastus lateralis force. But then as we go to this extreme case of increased femoral aneurysm by 40 degrees, we really see an increase in the joint load, a much greater slope between our muscle force and our joint load here. So the takeaway from this, these are preliminary results show that the effect of muscle forces on the patellofemoral joint load really varied across different levels of aneurysm, as well as different muscles, such as the rectus femoris or the vastus lateralis. So in conclusion, we employed a dynamic tracking MoCo problem to generate lower limb dynamic profiles for healthy as well as for femoral aneurysm models, and we validated this against experimental data. We found that through our Monte Carlo analysis, the joint load decreased, but load malalignment actually increased as femoral aneurysm increased. And then finally, our femoral aneurysm altered the relationship between muscle force and joint load, particularly for that case of the vastus lateralis that I showed. Further work to validate this model, as well as include more detailed patellofemoral joint modeling, such as contact, would greatly strengthen the work presented here. So with that, I'd like to acknowledge our funding sources, the Bucknell-Geisinger Research Initiative, my co-author, Dr. Mark Seeley, a pediatric orthopedic surgeon at Geisinger. Nathan Chaklis did some work on this as well. He's a medical student at Geisinger. And I'd also like to thank my research group at Bucknell, the Mechanics and Modeling of Orthopedic Tissues. And finally, I'd like to thank you for tuning in. Thanks, and I'll see everybody at the conference.